Can you see the white page?
Yes, sir.
So can anyone recall what we are doing in a heat equation? Just recall.
So we did Duhamel's principle.
Duhamel's principle. Okay. Duhamel's principle. Okay. So what is the heat equation? Just tell me. Ut minus Laplacian of u is equal to fx you want to solve, right? And u of x. U of x0 is some gx, right? Across 0t, that is in del omega. Across 0 if it's a thing, and u of xt some h of xt in del omega across 0t, right? Yes or no? Or we also from Rn case also we know that Cauchy problem. Rn cross 0t and u of x0 is equal to some gx cross 0. Okay. Okay. So you know how to solve it, right? Which plays an important role? Something called fundamental solution, right? Solution the heat equation of heat equation. Yes or no? Can you recall what is the fundamental solution? What is the fundamental solution? Huh?
So 1 over 4 pi t raised to n by 2 into e raised to minus mod x square by 40 for
1 by
t
4
greater than
pi
0.
t n by 2 e to the power mod x square by 40 and 0. So these play important role, right? Okay. And also we do some maximum principle. Do you remember? Yes or no? But for you remember we define a parabolic boundary. You remember? First class. Parabolic boundary. Do you remember this thing? Yes?
Yes, sir.
So what is that? Max, if it satisfies the uxt, omega closure cross 0t is equal to maximum of u of xt at something we call omega t. We call the parabolic boundary. What is omega t? What is omega t? The parabolic boundary.
So xt such that xt belongs to omega closure cross 0t
Cross?
minus omega cross closed 0t.
Not really. So you just draw the picture. This is your omega, let's say. Okay, this is omega cross 0t. This portion will be the boundary, the bottom one and this one. Omega cross 0t such that x belongs to del omega or t is equal to
0.
not this one. This is not this is excluded. This top portion is excluded. So this the bottom one and this surface. Okay. So, but here crucially we have used the fact that omega is bounded. If you remember the proof, we have used this fact that omega is bounded, smooth and bounded. So this plays a very important role, that omega is smooth and bounded. Okay, so this plays a very important role in the maximum principle. Now we will be doing a very important maximum principle for the Cauchy problem. That means we want to treat for when omega is bounded, this condition is relaxed. That means we will be studying these problems. Maximum principle for the Cauchy problem. Okay, maximum principle for the Cauchy problem. I will tell you what. So let U is C to 1 Rn cross 0. You know what is the meaning of that. C to 1 in means U is a function of xt. In x variable, it is a C2 function, and in t variable, in the interval 0t, U is a C1 function. Okay, you know what is the meaning of C to 1 omega t cross continuous Rn cross up to the closed and bounded. Okay, so U is, this means U is continuous up to the closed and bounded interval. Okay, and the open interval it is C1. Of course, in the open interval it is C1, it is given, but at the end point it is continuous. So it is continuous up to the boundary. Okay, C21 in t variable. Okay, solves, let this type of regular solution solves the PDE, the heat equation like this. In Rn cross 0t. Okay, and U equal to G on Rn cross. This is, now just look at it. Now it's not a bounded domain. It's the complete Rn. And suppose this fact, this is a very important assumption. Suppose U satisfies the estimates uxt is less than a e to the power a mod x square. X is in Rn, 0 less than t less than t for some constant a and capital A positive. Then this says that supremum of the function u of xt, which solves the PDE in Rn cross 0t, is equal to supremum of G in Rn. Is the statement clear? Just look at it. So we are doing a maximum principle for a Cauchy problem. That means now your omega is not bounded. Okay. So we will be studying this problem, ut minus Laplacian of u equal to 0 in Rn cross 0t and u equal to 0 on the Rn cross 0. There is no boundary of Rn, right? Now suppose you satisfy. So you can ask me whether this is a necessary and sufficient condition. I will come to that. Suppose U satisfies this condition, that u of xt is less than a constant e to the power a mod x square for some constant a and small a positive. Okay. So what it says that, what the hypothesis? The hypothesis says that U satisfies this equation. U satisfies this equation, and also U has this growth condition. That means U is less than a times e to the power mod x square. That means you can grow up to exponential. It's a large growth, right? You can go up to a exponential at Rn. So as x tends to infinity, the growth of U at infinity is e to the power a mod x square, right? So it can grow at an exponential growth rate. Okay, it's bounded by an exponential growth rate. Then the supremum of uxt is equal to supremum of G on Rn. Okay, so this is a non-trivial theorem because this omega, this Rn is not bounded. You cannot use the property of omega is bounded on all those facts, and G supremum can be infinity and all those things can happen, right? So this says that uxt should be equal to the supremum of uxt is equal to the supremum of G in Rn. Okay, we don't have this omega, any omega, it's the complete Rn result and it's a Cauchy problem. Okay, so this is very crucial, that it grows at exponential growth rate. Then you have that. Okay, I will come to that again. Okay, now let's prove it. So the proof is quite complicated. Not complicated, I must say that you have to be careful. A lot of analysis will be used to prove this. Okay, okay. And of course, another standing assumption is that this t is strictly infinity. Okay, t is strictly less than infinity. Okay, and then we see that. Okay, so first case one. So these constants are given, right? E to a capital A, that's c times less than c. E this constant a mod x square is given, right? E to the power a mod x square is given, right? So case one I am considering. Let us assume a small case time. That means when your t is less than infinity, I can take t very small. But which type of small? I will just prescribe that. Let us assume that 4at is less than 1. Why 480 I have taken? It will be very clear with the proof. So less than 1 or less than half will also work. Okay, this 1 is not less than 1. Any number less than 1 will work. Okay, so this 480 is not a very artificial thing. You will see that I am saying that t is very small. That's all. That's all. If your a is 1, so you can take t less than 1, and we will see how to deal with when t is greater than 1. Okay, that is the only thing. So I'm taking 480 is strictly less than 1. Okay. When then you can choose an epsilon positive. So this 480 is strictly less than 1. I can include epsilon also. Choose an epsilon such that the standard trick 480 plus 4a epsilon is strictly less than 1. I can always 480 plus epsilon is also less than 1. I can do always, right? This implies 4a of t plus epsilon is strictly less than 1. This I can do. Yes or no? Under this assumption, 480 is less than. This is yes or no. So this 480 less than 1 is not artificial. You just take t less than 1 or t less than half. I am taking that t is less than some constant. Okay. Okay. Is that clear?
Yes, sir.
All of you? Ankit, Kritika, Shammi, Chitram, Govind, Manish, Atharva, clear?
Yes, sir.
Yes, sir.
Okay. Okay, good. So 4a t plus epsilon is less than epsilon. Okay. Now define. So very nice analysis will be used. Okay. Define for y in any chooses for any fixed y in Rn, and for mu positive later it will be prescribed. Define for y in Rn and mu positive a function vxt. How I define vxt is like that. U of xt minus mu t plus epsilon minus t. T plus epsilon minus t. Okay, is that function clear? Yes or no? Just have a look on it. Is the function clear? Is the function clear? Yes or no? I just define a function vxt is uxt, mu is some parameter which will be later chosen, okay? And you fix some y in Rn, okay? X minus y whole square 4t plus epsilon t. That I have chosen. Is that clear? You can ask me why I have chosen this function. I will tell you why. Because who will tell me why?
Like we know u as we are bounding by u and
Exactly.
exponential that.
Exactly. So I have taken that function. Okay. Now now you check what equation V will satisfy. Any idea? What equation V will satisfy? You know what equation you satisfy. You can check very clearly that Vt t minus Laplacian of V is equal to 0. This equation will be satisfied by V. This is very straightforward. Can anyone tell me why? Why, anyone tell me? Huh? Why? Anyone? Anyone? Why? Huh? U satisfies this equation, no problem. And why this will be satisfied by this one? Huh?
So it's like
It is just
more
like
like
the
a
fundamental solution.
Exactly. This will be very similar to that of fundamental, because same thing. This is some constant minus t. If you just do the derivative with respect to t, small t, it will be a fundamental, because this minus will come out, right? This minus e to the power minus x minus whole square by 4t, 4 small t. So instead of 4t, I have t plus epsilon, which is a constant. So same. This is a fundamental solution. Okay, almost a fundamental solution with some constant. Okay, this will be 0 if you check it. Yes, very good. Okay, now we have a fixed y. Okay. So therefore, so this is satisfied. Okay, therefore, by maximum principle, in bounded domain, for any r positive, so this I have fixed some y. You just see, I have translate minus x minus y. Y I have fixed. So is a function of x. Y is just a fixed number. Not a number. It's a vector in Rn. So you have a neighborhood around y, r positive. For any r positive around a ball of radius r centered at y. Okay, we can use the maximum principle, right? Because it will also in Rn cross 0t. Now this same equation will satisfy. So maximum of V byr closure 0t is equal to maximum of V gamma r. What is gamma r? You know what is gamma r. You know what is gamma. What is gamma r? Gamma r is the parabolic boundary of byr cross t. Is that clear? Because in byr also it will satisfy this equation, right? This equation in byr cross 0t. Yes or no? Yes or no?
Yes, sir.
So byr also it satisfies. So maximum of V in byr is equal to maximum of V in gamma r. Gamma r is the parabolic bound. You know what is the parabolic. So this is the parabolic. This is the boundary, and this is the boundary, the parabolic boundary. Okay. So this part is not there, the parabolic boundary. Okay, clear? Okay, good. So therefore, by maximum principle, you have this. Now we will see how we will use this. This imply. So maximum. So y is a point in the. So this maximum of Vy. So in particular, this imply in particular V at the point yt is less than equal to maximum of V gamma r. Is that clear? This byr means all point here, right? So I'm just taking in particular, I take a point y. So vyt is less than, instead of x is varying in vyt, right? Vyt closure. Vyt less than maximum of v. Okay. Now let us see what happens to v. This is always less than maximum of v. Okay. For all y. For you know why, for y is fixed y. Now let x comma 0 belongs to gamma r. Then what is this point? X comma 0 is gamma r, means where this point lies. X comma 0. Huh? Here. This is the point. X comma 0 belongs to gamma r. So in the bottom boundary. You understand? Yes or no? Yes or no?
Yes, sir.
The x comma 0 is the point in this boundary. So let me draw again. This is your y. This is r. So okay. So I take a point some x comma 0. That is in the boundary, in this part of the boundary of gamma r. Gamma r consists of this and this part, the outer surface part. So I take first, you take a point x comma 0 from the bottom. Let's see what happens. X comma 0. Then what is Vx at 0? Is Ux at 0 minus mu t plus epsilon to the power n by 2. T is 0, right? You just, where I have defined the function, you just write down what is that. 4 of t plus epsilon. Is this a positive quantity? You forget about the minus. Is this a positive quantity? Yes or no? Because I have taken mu to be chosen later, mu is positive. Yes or no? This is a positive quantity. So this is a negative. So this is less than equal to u of x0. And what is u of x0 by the hypothesis?
GX.
Exactly. This is equal to gx. So what I have obtained? V of x0 is less than equal to g of x when x in gamma r, sorry, x comma 0 is in gamma r. So when I just use the definition v of x0, here you just put x comma 0, u at x comma 0, it's a 0 0, so this is a positive quantity, minus is a negative quantity, so ux is, then u satisfies this. You also know that v at the point yt is less than this and v of x0 is less than. So when the point is here Vx is always less than Gx. Vx0 is less than this. Now let us see what happened, what the V satisfies when V is at this boundary of gamma r. Okay? Let us see. This is very interesting. Okay. Now let xt belongs to del byr cross 0t. That means the lateral boundary of the parabolic boundary, lateral boundary. That means this part. This part. Okay? Okay. Del byr cross 0t. So what is the distance between x minus y? Can anyone tell me? What is the mod distance of x minus y mod?
R.
Yes. X minus y, because it is in the boundary of the y. Okay? Because you just see the picture here. So y is here, the x is here, the distance between y to r is, y to x is r. Okay. Then what is vxt? Vxt is uxt minus mu t plus epsilon minus t now we know that uxt is less than, always less than a e to the power a mod x square. Clear? Minus, I put t equal to 0. Is that true or not? Can I make t equal to 0? Is less than this? Yes or no? Uxt, I have used the bound, the hypothesis that uxt is less than this. Because it is given that uxt is less than this for all xt. Why this quantity minus of this quantity is less than minus of this quantity? Why? Who will tell me? Because you just think T minus epsilon, this is a triviality, minus T. This quantity is always less than T plus epsilon, or T positive, not negative. Yes, T positive, right? So 1 by T plus epsilon whole to the power n is also less than this whole to the power n. Then 1 by T plus epsilon minus T to the power n, sorry, n by 2, n by 2 is less than 1 by T plus epsilon to the power n by 2. Sorry, greater than. But when you're taking the minus, this minus will be okay. Is that clear? So this quantity, the minus of this quantity is less than this. And again, you use this fact again that minus exponential, this is less than T minus T. And okay, just triviality. You just use this type of elementary inequality. So is that clear, all of you? Why it is less than this? This quantity is less than this. Minus of this quantity is less than minus of this. Is that clear to all of you?
Yes, sir.
Okay, good. And it is trivial. That this is a hypothesis. Okay. So what we have now? Vxt is less than a e to the power a mod x square minus mu t plus epsilon to the power n by 2 e to the power x minus y square by 4 t plus epsilon. This we have obtained. Okay. Now we haven't used the fact that x minus y is equal to r. Now we have to use that x is in the boundary of del by, right? So what is mod x? Mod x, the triangle inequality says that x minus y, I can do is like this, x minus y plus y. This is less than x minus y plus mod y, which is x minus y is r plus mod y. So Vxt will be less than equal to e to the power, a constant is there, a instead of mod x, I write down less than equal to, so this is less than equal to mod y plus r whole square. Is that clear? I just take mod x square is less than what? Mod x is less than, so square will be less than square. Is that clear? Is that clear? This is less than this. Is that clear? Yes or no? I have just written mod x square
Yes, it's clear.
less than r plus 1. Okay. Because this is a fundamental analysis. Just think. Still I have minus mu times t plus epsilon whole to the power n by 2 e to the power r square. I just put equal to r. X minus y is r, so r square. R square by 4 into t plus epsilon. Here is the point where I will use that 4a t plus epsilon is less than 1. Remember, because we are considering the case when t is small. That means 1 by 4a t plus epsilon is strictly greater than 1. Yes or no? This I am writing, this imply 1 by 4a t plus epsilon is equal to 1 plus some delta, where delta is positive, for some delta positive. Yes or no? This is strictly greater than 1. That means this the t is fixed, epsilon is fixed, a is fixed, everything is fixed, less greater than 1. That means 1 by 4a plus t plus epsilon is equal to 1 plus some delta positive. This delta depend on a, t and epsilon. Okay? Is that clear? Is equal to 1 plus some delta. Is that clear? It is a number which is strictly greater than 1. So I am writing that this is equal to 1 plus some delta. Delta is positive. Okay? So now substitute this here. Okay? Substitute this here. You will get that this quantity, this will be less than a times e to the power a mod y plus r whole square. Okay? Minus this t plus epsilon n by 2 is mu times 4a 1 plus delta whole to the power n by 2. Just I use this equality. This equality here. 1 plus t plus epsilon by 2 is 4a 1 plus delta. That's it. Into e to the power 1 by 4. This one is e to the power r square a 1 plus delta. That's clear? So this is nothing but a e to the power a mod y plus r whole square minus. Now it's a very important observation. I will do that. To the power a 1 plus delta into r square. Okay. Now you tell me, you fixed y. What is the highest power of r? This if you break a e to the power a r square mod y square plus 2 mod y r, right? Minus mu, a constant, a 1 plus delta n by 2 e to the power a 1 plus delta r square. Okay? So here e to the power r square. What is the highest power of r? What is the highest power of e? What is the leading term here? You fixed for a fixed y. What is the leading term of this quantity? In terms of r, what is the leading term?
AR square.
E exactly. Into the leading term is e to the power ar square into e to the power this type of terms are there, y square plus 2 mod y r. Okay, minus mu. Here is the analysis. 1 plus delta n by 2 e to the power a 1 plus delta r square. What is the leading term of r here? Here. Leading term of r is this. Leading term of, so the competition is e to the power a r square from here, the leading term. And leading term here is a 1 plus some delta, which is strictly positive, r square. When r is very large, which is bigger? When r is very large, which is bigger? Out of this two term, which is bigger? What happened? Which term is bigger when r is very large for a positive? Which term is bigger?
Second one.
Second one. Because e to the power 1 plus delta is there. Here is a into 1. Here a into 1 plus delta. So this is much larger. So when r is very large, what will happen to this quantity? This quantity will be, as r goes to infinity, what will happen to this quantity? What will happen to this quantity for fixed y when r is very large? Mu is a constant, 4a is a constant, everything is constant here. When r goes to infinity, what will happen to this quantity? Where this quantity will go?
To minus infinity.
Yes, why you are thinking? Because this has a much greater growth. Definitely this goes to minus infinity. Definitely this quantity minus this quantity, because this quantity has a larger growth. Okay? Because this will be the dominant quantity. So this whole quantity will goes to minus infinity. That means this quantity is it can be arbitrarily small, right? So we have Vxt is less than minus infinity as r goes to infinity when x and t belongs to del p y r cross 0 t. So what I can say? So this imply Vxt I can always make less than supremum of G. Yes or no? This I can write. Can I write this? Why? If the supremum of G is minus infinity, then there is nothing to prove. There is nothing to prove, right? If supremum of G is minus infinity, then Vxt is less than equal to infinity. The supremum of G is if greater than minus infinity. So suppose it is greater than minus infinity. It might be some negative. So you can always, since Vxt goes to minus infinity, you can always make Vxt is less than this for sufficiently large R. You take that R for which Vxt is, so let's say supremum is minus C or something. Let's say supremum of G is minus C. You can choose some large R. These are very, very large, such that Vxt is less than minus C. That's it. You can always do, because Vxt goes to minus infinity as R tends to infinity. That means you can always make Vxt is less than minus C. This is the definition, the Vxt less than minus infinity, right? And if supremum of G of xn is minus infinity, there is nothing to prove. So Vxt is always less than equal to supremum of G. Is that clear? Is this analysis clear? This is very interesting analysis. What happened? Manish, Atharva, Ankit, Kritika, Shammi, Govind, Chitram, and Nikita. What happened? Is that clear?
Yes, sir.
Manish?
Yes, sir.
Ankit? Govind?
Yes, sir.
Kritika?
Yes, sir.
Shammi?
Yes, sir.
Clear? Absolutely clear? Chitram
Yes, sir.
or Nikita? Is that clear?
Yes, sir.
Because this term goes to minus infinity as R tends to infinity. So you can always find some R very large. You can choose R large enough such that Vxt is this. Okay. You can always do that. Okay. So what happened? So what? So we know that thus, because now you take a very large ball, thus we take a, thus it implies with this choice of R, choice of R means for which Vxt is less than, supremum of Vxt is less than supremum of G for large R, okay. With this choice of R, we get some R, you can fix R equal to some R naught or something like that. We get Vyt is less than maximum of V in gamma R. R means that R. For this choice of R for which Vxt is less than supremum of G. Okay? Is less than equal to supremum of G. Now what is this happen? What is Vyt? Now you just write down what is Vyt. Vyt is nothing but U of yt minus mu t plus epsilon minus t whole to the power n by 2 is less than, because I just write down the definition of Vyt is less than supremum of G. Now you can take, since it holds for any mu positive and G is independent of mu. Now taking mu tending to 0. So mu tending to 0, this will happen that Uyt is less than supremum of G. And you remember, I have chosen Y to be any arbitrary point in Rn. So this happen, we can do this thing for any Y. So Y is arbitrary. So thus this implies that supremum of U is less than supremum of G. Since supremum of G, since Y is arbitrary. Is that clear? The proof is clear. So this proof is done provided that 480 is less than 1. Now tell me, suppose for if 480 is greater than 1, or what we'll do? Anyone? What you will do? What you will do? Just think about it. T is some fixed, T is less than infinity. So what you will do? Any idea? So you have done for when 480 is, so let's say T. You have done for when 480 is less than 1. So what you will do? But if T is very large, what you will do? You will just subdivide the interval of length of where. So you subdivide 0 to T1, T1 to 2T1, like the, up to go to up to T. Okay, so that each interval is of length. That means this interval of length 0 to means 0 to T1. T1 4a T1 is less than 1. Again T1 to T1 is less than 4a T1 is less than 1. So in the general case, this is nothing. In the general case, when 4a is less than 1 does not satisfy, we apply the result, the above result on the time interval etc. You understand, right? For fixed, you can break always of this time interval. Do this here, do this here, and then okay. Is that clear? Okay. Now we have important corollary. Corollary says this: let G is C of Rn, F is continuous Rn cross 0T, then there exists at most one solution. Of the problem in Rn cross 0T satisfied. This is important because we cannot apply maximum principle unless you have this condition. For some positive. Okay, so this is that. So what you will do, anyone? This equation has at most one solution. What you will do? Anyone?
We take two U1 and U2 to be two solutions and then use the maximum principle to prove uniqueness.
Always we remember that you have to apply U1 minus U2, you have to satisfy that U1 minus U2, you should satisfy this condition. Of course, because U is less than, so mod of U is less than mod of U1 plus mod of U2. That is less than some constant A tilde e to the power n mod x. Otherwise, you cannot apply, because this is a very important lemma remark I will be doing now. Of course, I will not prove this or something. This is a very important or a fundamental thing in heat equation is that this remark. If you don't assume this condition, right? then this maximum principle, this corollary is not true. There are examples, very simple example, the equation ut minus Laplacian of u equal to 0 in Rn cross 0 infinity and u equal to 0 in Rn cross has infinitely many solutions. Many solutions besides u is equal to. So of course, capital U, this u is identical to 0 is a solution, right? Clearly it satisfies this equation, but it has infinitely many solutions which grows very fast. Very fast. That means it has some exponential growth, like at infinity, not at, because otherwise u equal to 0 will not satisfy. So it will be which grows very fast, which grows to infinity, at infinity. Okay. So it's like that. So there are infinitely many solutions of this simple equation if you don't assume this condition. Okay. It's more than which grows faster than this at infinity. Okay. It grows faster than this. Okay. Other, if it less than this one, then automatically this will be this satisfy and u is equal to 0 is the only solution. But if there are solutions which grows faster than e to the power a mod x square. Okay. At infinity. Okay. So these are an example. You can see Fridge zone. Okay. Another, so this is the maximum principle. So we have done the maximum principle in bounded domain, which is not difficult, but this in also in a Cauchy problem, Rn cross 0 theta. Of course, plus some, for this we need some assumption on growth of u, Okay. Okay. Now one more properties, it's a very important property which I will not prove. This is a quite complicated proof and it uses something called modifier and all those things. I have not proved that, but at least a statement will be enough for you that let omega is a subset. This is a regularizing property. It's a beautiful property. Let omega be any subset of Rn, be open. And u is C to 1 omega cross 0 t. Okay, solves the heat equation. Solves the in omega cross 0 t. Then u is C infinity. Okay, it solves the equation ut minus Laplacian of u equal to 0 in omega cross 0 t. It's a heat equation. Okay, then u is C infinity. That means any solution, C2 solution is of the heat equation is regular. That means it is always C infinity. That means so because it is only given u is continuous, u is C2 in x variable, and it is C1 in t variable, but and it satisfies this equation. But you can show that it actually this is u is C infinity. That means u is a smooth in omega x variable as well as in time variable. Okay, just from 2 to 1, from 2 variable, the degree of smoothness is 2. That means it is smooth. It's just C2 function. You can prove that it is a C infinity. All this if that means whenever the heat equation regularize the solution, it's called regular. That means if u satisfies this equation, then u is a smooth solution, C infinity solution, like the Laplacian u equal to 0. Remember, u is C infinity then. Okay, heat also has this property. Okay, u is C infinity. The proof is very similar to that. You have to modify it and do it, but it's quite complicated because of the time variable. Okay, the idea is same, that you have to convolve with the exponential and all those things. Okay. Okay. So I'm not proving this, but this is for your information that it regularizes the heat equation always has a smooth solution. Okay. Okay. One more thing I will do, and then I will solve. This is the last topic I will do: energy in heat equation, energy methods. You remember we did it for the Laplace also. Let us start with a simple problem. Let omega be a bounded domain with C1 boundary. Then the problem ut minus Laplacian of u equal to, just now we have discussed this, but I will prove in a different way. Has let omega be a bounded domain with C1 boundary. Then the problem ut minus Laplacian u equal to f and u equal to g on gamma has at most one solution. Okay, just now we have done this by maximum without using the maximum principle. We will do just using energy methods. Let us define a, suppose the same standard trick. Suppose u1 and u2 are two solutions. Let u is equal to u1 minus u2. Then we have ut minus Laplacian of u equal to 0 in omega cross 0 t and u equal to 0 on the parabolic boundary. Now you define the energy. This is called the energy. U square xt. The same thing we have done in the just for t, you define u square xt dx integral over omega. Okay, so e prime t will be omega 2u into ut dx. Now what you will do? U satisfies this equation. So what I can substitute ut? Huh?
Laplacian of t.
Exactly. So E prime t is equal to 2 omega u ut. U satisfies this equation means I can substitute u Laplacian u dx. Then what I can do?
Use integration by parts.
Excellent. This minus will come. What will happen to the boundary term? What will happen to the boundary term?
0.
Why? Because the
So u
parabolic
is 0.
boundary, because the parabolic boundary also has this. Because del omega cross 0 t. It also parabolic boundary consists of this also, right? So there will be no term. So minus 2 omega gradient of u square dx. So this quantity is less than. Yes or no? Yes or no?
Yes.
Okay. What is E at 0? E at 0? Just think about E of 0. What it will be E of 0? It will be u square x comma 0 dx. What is u square x comma 0? Kritika?
0,
0. Why?
because it's the
U
bottom.
equal to 0 in omega cross 0. Also because it's a 0 in the parabolic boundary also consists of the bottom. Bottom means this one. So this is 0. So E of 0 is 0. So we have two quantity now. E of 0 is 0 E prime of t is negative and Et is always non-negative because it is. So what I can conclude? A function f0 is 0, f prime t is negative and ft is positive. That means
maximum at 0.
what will be Et? What will be Et? Ben?
0. Identical to
Yes,
0.
for all t. Come on. For Et equal to 0 for all t. That means integration omega u square xt dx is equal to 0. That means u is equal to 0. Means u1 of xt is equal to u2. Done. Just using this fact that energy method, we have proved that it has at most one solution. You know why I'm talking at most. It might happen some PD will not have not a solution. That is why I've used the term at most. Okay.
And sir, how one thought that we have to choose this particular integral?
Yeah, because this is an energy. I already told you that this is something called Lagrangian. So always there is some Lagrangian associated with the PDE Laplacian of u or ut minus Laplacian of u equal to 0 or something like that. I always say that this is called energy. Is the energy of the solution. Okay, this is always u square. This comes from the physics, right? This is the Lagrangian. So whenever there is some equation, you can always think about what will be the Lagrangian. That you remember that JUI we have chose like this, that half gradient of u square minus integral f of u. You remember when I choose the
Yes, sir.
so that then I said that how to think of it, that you just multiply this with u, okay, and then take the integration by parts. Then it will be gradient of u square, this term. Just think, this is the way you should think about it. And you just rest ut because you are doing at 0, so ut will be 0. So that will be the gradient of u square. So when you want to derivative something, you must get a gradient. That means you have to choose this u square kind of energy. You understand? Or you can say this is a kinetic energy, half mv square. M is, let's say m is a constant, okay, some 1, mass is 1, so you half u square or kind of thing, right? So u square, you now integrated, that is the kind of velocity or something like that, okay? So that is why called energy methods. They are called energy methods. This is the energy, associated energy, because same thing we have chosen in Laplacian also, okay? Okay, now is the last theorem. The same with the energy method. It's called backward uniqueness. This is the unique property which has with the backward uniqueness. Ut minus Laplacian of u equal to f in omega cross 0t, and u equal to g on del omega cross. This is not a parabola. I am taking the top also. Suppose u1 and u2 are two solutions to the above problem. To the above, this is a very interesting phenomena, problem star. So let's u1 and u2 be the two solution of this equation. Ut minus Laplacian u equal to f and u equal to g. Okay. If, this is very important, if u1 at x t naught, at some point t naught, if u2 at x t naught are equal at some point for all x in omega and for some t naught, then it will be equal for all t which is less than t naught. That is why it's called backward uniqueness. I will tell you. Then u1 is equal to u2 in omega cross 0 to t naught, not up to t. So what is, just draw the picture. So let's say this is your omega. at some t naught. At some t naught, we have u of x t naught is equal to u1 to solution x t naught. Then u will be u1 of xt is equal to, this is a non-trivial theorem, xt for all t less than t naught. Yes. So in the backward, that is what called backward uniqueness. Backward means this is t naught backwards. This is backward in time. So t naught less than t naught. That is why it's called backward. So for all t less than t naught, if it is equal at some level, then it will be equal at all level below t naught. This is an extraordinary theorem. That is a unique property the heat equation has. Suppose it is equal at some level, the two solutions meet at some level, then you will have a uniqueness all along the backward direction. Then you want, but at the level of t naught. So you cannot say what happened here, but less than here, u1 of xt is equal to u2 of xt. Is that clear, this statement? Is this statement clear to all of you? Is that clear?
Yes, sir.
At least the statement is clear. Huh? So if it equal to t naught at some, because u is a function of xt, u1 is a function, u2 is a function of xt. If at some t naught it is equal for all x, at some level of t naught it is equal, then it will be equal all along below the t naught. This will be, this imply u1 of xt will be equal to u2 of xt for all t less than equal to t naught. Is that clear? Is that clear?
Yes, sir.
You want to see the proof or you don't want to see the proof? What? Or I should leave the proof. What do you want? Manish, Atharva, Ankit, Kritika, Shammi, Govind and Chitram. What do you want? Huh? Tell me quickly. You want me to prove or the statement is enough for you? Huh? Shammi?
So we will try to.
Okay, I will do it fast. You just have a look. Proof is not that difficult. Do you know what is a log convex function? Log convex function. Do you know? Anyone? Log convex function. What is the meaning of that? You know what is a convex function?
Yes, sir.
And what is log convex function? The function x going to log of fx is convex. Means log of f of lambda log of fx plus 1 minus lambda log of fy. This is log of f lambda plus log of f lambda log of okay. Then log convex function will sorry g function g of x equal to log of fx is convex. Okay, is that clear? So log of this is less than log of f lambda x into log of this. That means f of lambda x is less than f of lambda x into fy of 1 minus lambda. Is that clear? Huh? This is called log convex function.
Yes, sir.
Log convex. This I will use. Okay. Let's see. Write down the same thing, proof. W is U1 minus U2. Define your favorite energy. E prime T is 2W WT. Okay, again you do the integration. E W satisfies the equation. You know what's the equation. So E prime T is minus 2. You know this. Gradient of WXT. Okay. Now what you will do? You do the U double derivative of T. This will be minus 2 gradient W gradient WT. Okay. So just this will be 2 into gradient W dot gradient of WT, the derivative with respect to T WT. Now what you will do, this will be now double derivative is nothing but E, this is a E double prime T is now is minus 4 gradient W dot gradient W with respect to T dx. Now use the integration by parts. Minus, it will become 4, this will be W. So this is Laplacian W into WT. Why there is no boundary term? You know why. Okay? You know why there is no boundary term. So that means, and what is WT? WT is equal to, what is WT? Huh? What is WT?
Laplacian W.
Ah. Laplacian of W. This is Laplacian of W. So that is 4 omega. So you have E double prime T is equal to this. Just hold on. Hold on in this equation. You just consider another. This is nothing but integration by parts you do. Integration by parts. Gradient W, this is nothing but gradient W, gradient W. You just take the Laplacian W minus. Again, it's 0 because W equal to 0 on 10 omega. Okay? No boundary term. Do you know Cauchy Schwarz? Integration FG less than, you know this? L2
Yes,
GL
sir.
Felder inequality. This is your function f, this is your function g. Minus is take the modulus. Okay, less than, this is less than omega w Laplacian w dx. Okay, if you do that, it will be omega okay. So here is number 4 is there. No, okay, okay. What is this? So earlier we have equation 1. E prime t is this, and what is et? Et is this, and what is E prime t is this. Okay, so E prime t whole square from here. E prime t whole square, if I do, this will be 4 square, right? So this is equal to 4 gradient. Okay, so you this resembles like this. Okay, this is less than, just use this property. 4. So this is E prime t whole square. What is this? Et. And what is this? Just think here. Equation 1. If double prime t is 4 into Laplacian integral Laplacian w square. This is Laplacian. So I have a inequality in E prime t. What is that? E prime t. Listen, now problem in analysis. Et for all 0 less than t. Is that clear? This is just a computation. There is nothing. Is that clear? This equation inequality is clear. How I got? It's nothing. This is just a Is that clear? Is that clear? Just think about it. Just think about it and tell me, is that clear or not?
Yes, sir.
Is that clear? Tell me.
Yes, sir.
Clear? Now using this inequality, you have to show that if I define ft as log of et, this ft is a convex function. Why? To prove ft is a convex function, what you have to do? Any idea? You have to show that f prime t is. There is a theorem that f prime t is greater than equal to 0 if f is C2, if f is C2, if f is C2, then f prime t is greater than equal to 0 if and only if f is convex. This you know, right? Rudin's exercise. Do you know this? If f is a C2 function, then f prime t is greater than equal to 0 if and only if f is convex. That means f prime greater than equal to t is 0, then it implies it is a convex. If f is a convex, then f double prime t greater than equal to 0. If and only. Know this? In analysis problem, this is a very nice analysis problem. Do you know this? Yes or no? Tell me yes or no, then I will tell you what is that. Do you know this? You can try as an exercise. It's not difficult. You can try. Okay? You assume f is a C2 function, then f prime t is greater than equal to 0 if and only if. There is, in fact, one dimension is very easy. In fact, this is true for n dimension also. If d2 of f at the point x is non-negative definite, then f is a convex function. In fact, we don't need C2. If d2f is greater than equal to 0, almost everywhere says that. That's a very, very deep theorem. It's called Alexandrov theorem. So don't worry about that. This is just a one-dimensional result. This f prime t is greater than equal to 0 if and only if f is convex function, and assuming f is a C2. Is that clear? You will try this problem? Yes or no? It's a very nice exercise. Okay. So using this, you show that f double prime t is positive of this function. Here you have to, because if you do the derivative of f prime t, you will end up with like this: e double prime t by et minus e prime t whole square minus et. Okay, end up with this. This is f prime t. F double prime t. If you compute this, then if you multiply this, then you will have e double prime t into et whole square minus E prime t. This is a numerator, denominator is et whole square, right? And the numerator e double prime t into e prime et whole square minus e prime t. Use this fact. Okay. And et is always positive, which is a gradient square, and et whole square, prime t whole square is all et square is always there. So sorry, et square. So greater than equal to 0. So yes, greater than equal to 0. So this ft is a log convex function. Okay. Once you have a log convex function, you can use this. So t going to log of t is convex function. Then log of e of 1 minus lambda, 1 point you take 0 plus lambda t is less than 1 minus lambda log e of 0 plus lambda log e of t. Log of e of lambda t is less than now taking t tending to t naught. What is e of t naught? Can you tell me what is e of t naught? Hmm? What is e of t naught? What is et? Just think. What is et? What is e of t naught? This is omega square t naught means u1. What is omega x t naught? That is u of x t naught minus u1 of x t naught, u2 of x t naught. And what is the hypothesis? Huh? What is w of x t naught? u1 x t naught minus u x t naught. What is the hypothesis? That means w square is 0. So e of t naught is 0. So if you do that, then e of lambda t naught is less than equal to e of 0, something e of 0 into e of t naught. This is 0. So e of lambda t naught is, this implies e of lambda t naught is less than equal to 0. Also, you know that e of lambda t naught is non-negative. So this implies e of lambda t naught is 0 for all lambda in 0 to 1. And this implies lambda t naught, lambda belongs 0 to 1. That means e of t is equal to 0 for all t, because lambda is 0 means t naught, lambda 1, lambda 0 is 0, lambda t naught, lambda when lambda is 1 t naught. So between all 0 to t naught, et is 0. And this implies u1 of xt is equal to u2 of xt for all t less than t naught. So the backward uniqueness. Oh, I understand. This is I prove it very fast because this is a log convex and many things are there. So you don't if you want to just hold on with this. It's a quite interesting theorem, but at least you should know the statement that if at one level t naught, if it's equal, then it will be equal at all less than t. Okay. It's a very unique property, only hold for, which is only true for heat equation. Okay. So this is very interesting that if some solution is equal at some t naught, then it will be always equal below t equal to t naught. T is less than equal to t naught. Okay. The proof is using the energy method. The only, I think, if you are this log convex function. So you are not familiar with this property, just tell me honestly that that f prime of t is greater than or equal to 0 if and only f is convex. You are not familiar with this?
Yes, sir. We have seen it in calculus.
Just I am using that. Just use f prime t will be derivative of this, and using this fact that e prime t square, you prove that this is actually greater than or equal to 0. Hence, it's a log convex function. And once there is a log convex function, you just apply the definition of log convex function. Just apply the definition of log convex. Once you have done with the log convex function, it's not difficult, but you have to be careful. Okay, I think that's all. So it will not be in the examination because these two lectures, this lecture number, this today's lecture and the next day lecture will not be included in the examination. Okay, major. So the syllabus will be 1 to 21. Okay. So do you have anything to ask me? So of course Thursday we will have a class. We will do something on wave equation. Then I will. Of course, this will not be included in the syllabus, but at least you should know what is. At least you should know the name that there is something called wave equation. Okay, I'll do it fast. Very simple thing I will do and finish it off. Okay. So anything else you want to ask me? So your quiz 2 is graded now. Of course, you have put some regrade. I will do it today or by tomorrow. So request will be taken care, and I will give you the schedule of the examination. Schedule 22nd, and major will be of 40 marks. The syllabus I have reduced this to 2 days lectures. I will not ask the wave equation because last class I will be doing the wave, so I just leave that. And this today's lecture also I will leave that. So there will be questions on heat equations, but before this lectures number 22. Okay, and Laplace will be there, and of course the first part will be there, that which you are comfortable, I think. So that's all. So do you feel this PDE course difficult? Just tell me honestly. Atharva.
So somewhat difficult, but
Ankit.
Yes, sir. It is difficult than my expectation. Yes, sir. It is more difficult, sir.
Pritika.
Yes, a little bit.
Difficult. Okay. Shammi.
Yes.
But at least you have understood something. Then
Yes,
it will
yes, definitely.
Okay. Chitram.
yes, sir, difficult, sir.
Sanjeev.
Yes, sir. It's
Because at the beginning of the course, I said no. There will be some measure theory, some function analysis, some differential geometry, little bit of idea of differential geometry, and all those things will be there. Okay. So don't worry. Whatever you have learned, it's okay. Okay, but at least you should believe that PD is it's not solving. Okay, it's more than that. It's very analytic and more geometry and more analysis, measure theory, and even this is called classical PD. Okay, so these are not nowadays. It's a very old-fashioned thing. So there is something called modern PD, which is more function analysis. Okay, so whatever functionals you are learning in this course, everything will be applied in modern theory of PD. So there is some course, modern theory of PD, which is completely a function analysis. Okay. So PD is a combination of, this course is a combination of measure theory and little bit of implicit function and inverse function theorem and little bit of surface idea and all those things. So at least you should understand a little bit of that, at least something. That means just solving is not a motivation of this course. Some analysis, basic analysis is needed. Anyway, so next class I will do a little bit of wave equation and then I will stop, and that's all. Okay, thank you. Thank you.